So, Devicenet. All right. This, like half the things we're talking about, is starting to become an antiquated technology. All right. It is not something that is like, oh, we're going to put a new system in, let's use Devicenet. No, new systems, you're like, let's use Ethernet. All right. However, as I said, like everything in this class, these systems are out there, and they're going to be out there for years to come. All right. Industrial equipment is not like your house where every 3 years you're like, yeah, I could buy a new computer. You sell your old one, you buy a new one. The world of industry is not like that because A, updating your equipment takes time. That's time is money, so don't want to be down for that long to update equipment. B, you've already spent thousands, if not millions of dollars on this equipment. Now you're going to, every few years you're going to pay to upgrade it. If things still working fine, might change it. All right, so just like everything else. But a quick little bit of history for you. Devicenet was developed by Alan Bradley. Probably not a surprise there since I already mentioned Alan Bradley. But Alan Bradley was the one that started this. And it's been around since the late 1990s. So been around not super long, 30 years. Somewhere around maybe 30 years, depending on how late. But anyway, it is a low-level device-oriented network. And what do I mean by that? I mean, this is designed to interconnect lower-level devices, sensors and actuators, with the high-level devices like controllers. All right. So, yes, for those we just played with PLCs, we had a non-modular PLC, right, which meant that PLC had its inputs, it had its outputs, it had its controller, it had memory, it had networking, it had everything it needed. You can write your program on it, you could run your program, all of that, all on that one device. And that, in theory, you buy one and you're done. You can go install it on something and you're fine. In fact, if you look at our little assembly line over there, there are 5 PLCs, just like the one we used running on that. Now, those do actually have a little extension module. So while it is technically, I would qualify that one as a non-modular, the Siemens 1214C AC/DC relay. It does have capabilities for expansion. And the reason I qualify it as non-modular is because you don't require those modules unless you need more I/O. All right. However, a traditional module would be like you buy your CPU, then you buy a power supply, then you buy your inputs, then you would buy your outputs, then you would buy your communication, then you would buy other specialty. So each one is its own little individual card that you'd slap into the rack. All right. So modular versus non-modular. But anyway, if you have a modular or non-modular and they're networked and you're like, I need more I/O, you could slap another card on there if it's got that capability, and then you could run your input wires 500 feet down your assembly line to wherever they are. That's a lot of wiring, and copper is expensive. Every day it's getting more expensive. All right. So instead, what you could do is you could say, well, I'm not going to run every one of my I/O. I need 20 more inputs and outputs down 100 feet down the line. Well, that's at least 20 wires plus power or ground, connection back to the PLC, yada, yada, yada. So, you got maybe 20, maybe 25, 30 wires that you have to run that way. And depending on what those devices are, those could be, a significantly large wire. Not like a 40 gauge, but maybe like a 20 or 15 or something like that. So it has some physical size to it. Or you could buy a little module that you put down there, buy all your I/O, and all you run is your communication wires back. All right. Anytime we're talking about remote I/O, that's what we're talking about. You'd have this module, which I wish I had a great example of, which I do not, unluckily. But we could pretend, if my, yep, all right. But let's go ahead and hit this button. So we could pretend that this PLC, where my Ethernet cables are, is my modular bit. Well, that I could take off, and maybe, it's like this contactor now. Well, this I would just put wherever on the assembly lines closest to all those I/O that it could handle, and I just run a Devicenet wire to it, or Ethernet, or whatever the interface type is, serial, parallel, whatever it is that you would like. And you would just run that. So now for Devicenet, we've got 4 wires. 2 signal, 2 power. And you don't necessarily need to run both power. You always need to run that ground wire. All right? You guys remember back at the beginning of the semester, we were doing the projects with the Arduinos and just trying to send serial data between the two. And the one group were using 2 separate laptops, which is what I wanted to be done. And we had the TX hooked up, we had the RX hooked up, and we couldn't get freaking messages to send. I was like, what's going on? Finally, it took me a while, but finally I realized there's no ground wire. So there was no loop for that signal to come back on. So once we hooked that up, it was good. So ground wires are always required for communication because you need some way for that to complete the loop. All right, it's not one direction. Now, if you're talking about fiber optics, which is light-based, that's a whole different game. But electrical-based stuff, you got to have a ground loop. Not a ground loop, a ground connection. But anyway, so yeah, 2 wires. They can be very small wires because they're not carrying a lot of current. They're just carrying signals. And that's it. So 3 wires, I guess, with the ground. Or you could throw the 4th power wire in and not have to have a power supply at the other end. So a little bit of give and take going on there. Now, this is based on CAN. All right. Any of you guys heard of CAN before, other than me saying the word CAN? You have?
Yeah, remember CAN bus?
CAN bus, yep. CAN bus, all right, which is a controller area network. All right, so this is something that was actually designed for the automotive industry. Same idea. Instead of having all of these wires, big wires, we have to run back up to our main computer at the front. We have a CAN bus in our car that you can just run like the taillights to a module in your back of your car, and your headlights to a module in the front. Your door locks are their own CAN bus, and this is its own, and that's it. Everything its own damn CAN bus anymore. So it made wiring simpler, but it made troubleshooting harder because now you have to get on the CAN bus. All right. And then also, because of that, made like ways you can hack your computer, not your computer, your car. People sell little modules that you can put between your dash cluster that has all your gauges on it and the rest of the CAN network. So when certain messages try to get sent through, it erases that message and sends a slightly different one, like mileage. So it's like your odometer says, yeah, there's only 30,000 miles on this car, but that little device is taking off 100,000. So it's actually 130,000. They're out there. They are nowhere near legitimate. Don't do it. But it's just kind of interesting that like that type of thing exists because of the CAN network. We wouldn't have been able to do it before that. Now, before that, they would just hook a drill up to it and run the speedometer, like just hook the cable up to the drill and just run that thing until they got it to the mileage they wanted. They might have to run it, and roll it over to then roll it back, but it's still something that's out there, which sucks, but it's the game that gets to be played. But anyway, CAN is a variable multi-byte format that's on the CAN message frame, and it's well suited for this task because more information can be communicated per message than with bit type systems. All right. If we talked about serial, you remember that it was just like, okay, we need to send a start bit and then all the data bits, however many there are. Then we need to send a parity bit if we're sending it. Then we need to send our stop bits if we're how many stop bits are we sending? So all of a sudden it was just like, we got all these extra bits hanging on the end of there. Where CAN, we're not going to have quite as many. Now this is now a ODVA, which is an Open Device Network, an Open Device Net Vendor Association. This was released to them in 1994. All right, so pretty early on in the whole Devicenet world. So this is now an open network. So in theory, anybody can create stuff for it. Alan Bradley used to hold all the secret sauce and stuff and said, "This is our network. You can't use it." And now they're like, "Yeah, okay, you guys can use it." So other companies can now create Devicenet networks or devices if they would want to. Not required to, but if they want to. As I said, kind of a dying thing at this point. The ODVA does issue Devicenet specifications. So as the years go on and they tweak things and they change things, these are the ones that are telling, hey, everybody, here's a new rule set type of thing. This is version 15.6 type of thing. They're also the ones that are ensuring compliance. So making sure that you are following the rules of how the devices are supposed to communicate and those types of things. They also will offer technical assistance for manufacturing wishing to implement Devicenet stuff. So it was kind of a nice thing that they did. Having said that, Arduino is like my go-to microcontroller, and I'm like, can I do Devicenet on an Arduino? And you ask the internet that, and they're like, no, it's too heavy of a process. So it's very computer intensive. So you can't just have a little Arduino running it, which I was very disappointed at. I'm like, why not? Like, let me just look up a little Arduino here, and we can be good to go. Like Profinet, no, can't do it like Profinet with Siemens. So I was very disappointed. So Devicenet supports up to 64 nodes. So 64 devices. All right. So considering, where networks used to be, that was a nice pretty penny. 64 of them, one being the master, 63 others. We traditionally use a 4-conductor cable, so that again is our 2 signal wires and our 2 data wires. Skip something. Going back to the nodes. The nice thing here is any node should be able to be removed without affecting the trunk. So without affecting anything other than the communication. So like, whatever node dies, you should be able to yank it out, move your terminal block or whatever to another one, plug it back in, and be good to go without touching anything else. You don't have to like power the system down. Unhooking that's not going to kill everything else on the network. It's just you should be able to like plug and unplug really simply, which is nice. And you'll see why that works in a little bit when we talk about the connectors and things. So connector cables. Traditionally, we're using round or flat, so we're using like almost like a ribbon type cable or a round Ethernet-esque cable. This does support a bus topology, which is a trunk line with a drop line, and this allows branching, which is good. Again, that's how we can get away with removing devices and not screwing up the whole network. So we have branches and things like that going on. It does have reverse wiring protection, so if you screw up and wire things backwards, you're not going to fry things. Everything should have reverse wiring protection built into it as far as I'm concerned. All right. I don't understand why devices nowadays don't have this. Like, oh, if I plug the power in the wrong way, we're going to fry something. It's like, put a freaking diode on it and be done with it. Yes, it's going to drop you maybe 0.3 volts. But to me, that is well worth the power loss to make sure that when I'm like assembling something, if I plug it in, I'm not going to burn up a $1,000 device. Now, having said that, you're like, well, 0.3 volts of a loss, whatever power loss that is over however many years, you're going to be running this thing constantly. And that's some actual power then. You've used some good electricity at this point. I'm still saying it's worth the power loss as a technician point of view, but to each their own. So they won't get damaged. We have some different baud rates available. We have 125, 250, and 500 kilo. Those are all kilo, not just the 500. The nice thing here is it does not, whatever your installation, it doesn't have to support all the baud rates. Really, that it comes down to is the baud rate is specific to the distance that you're running. So if you're running 125K baud, you can go 500 meters or 1,600 feet, roughly. All right. If you're going 250K, you get 250 meters or about 800 feet. And if you're running 500K, the fastest, you only get 100 meters or 300 feet. All right. Now, the more devices, the higher the baud rate's going to be. Or the more important having a higher baud rate might be. Because if they're all trying to send information out constantly, you need to be able to send information quicker. So that way they're not freezing up the line. So kind of important in that aspect. Over on the right, I have a very, very blurry image, but it was the best one I could find. But we're talking about the OSI layers here. All right, this open systems stuff, man, we've just been like hitting this like crazy. Like every type of system seems to use that stuff. It just drives me nuts. I hate it, but again, doesn't really matter. So for our purpose here, CAN bus, that is actually traditionally down on layers 1 and 2. That is our transmission medium and our medium attachment. So how we're attaching all these things. Devicenet, that's actually more on the 3 and 4. So that's the physical signaling and the media access control. 5 through 7 is part of the chip network. CIP. Yeah, CIP. And that is the Common Industrial Protocol. So this is another one of those like kind of things that we're trying to like standardize. We haven't got everything standardized going on. So yeah, the OSI model, it just comes back again. So for communication, if we're going to have multiple devices on the network, we obviously need some sort of ID. It's not just me talking to Trevor. There's four of us in the room, so I got to tell you who I'm talking to before I talk to you. All right. So this is kind of like Ethernet. These traditionally are going to be predefined, and the reason we're predefining them, A, so they're always in the same spot. B, it lowers resources, but we don't have to have a device sitting there going, hey, there's a new device, here's a network, here's an ID address. All right. And C, the ordering matters. All right. So the lower the ID number that it gives you, the higher, not that it gives you, that you assign, the higher the priority that device has. So, if you have a device 1 through 64, you don't want your highest priority device to be 64 because according to the system, that's the lowest priority. So you want to keep things on the lower side when they have a higher priority. Those might be things like safety relays or e-stop buttons, those types of things. You're going to want to keep those on the lower side of things. And for me, it's really quite interesting how these communicate because they have the line be high, and when they pull it low, that's a 1. That seems to be how most things are working, right? We go from, it's kind of inverted logic. But if two devices were to start transmitting information at the exact same time, since they're pulling it low to go high, the lower device number wins because it's pulling the lines and things like that. So it's just weird. We'll kind of talk more about that another day, I think. But anyway, we've got two main types of messages, unconnected and connected. That to me is really weird. How do you have an unconnected message? All right. So unconnected messages have a special virtual access port. All right. And this allows to send info to a device without actually connecting to it. So normally it'd be like, hey, Trevor, and I'd be connected to you, and I'd be like, give me this information. You'd be like, okay, here you go, and yada, yada, yada. Well, this access port doesn't make me to say, here, connect to me, talk to me. It's just kind of like sending information to you. This is really only used for creating and deleting connections. So setting up the Trevor's here, Dave is here, Cam is here, Bob is here, Joe is here, whatever the case. It's, all right, I'm connected to you. I can send information. I can get information. I'm expecting messages, whatever the case is. All right. So connected messages are our main type of messages here. And there are three main types of connected messages. Those would be your explicit response / requirement type messages, your IO messages containing formatted data, or your cyclic messages, which is a change of state or a response to a poll type of thing. So those are our three main types of messages. Now, inside of that, we've got some other messages. We've got peer messages. And unluckily, this is not the typical message that's used here. The typical one is explicit. So let's talk about that one. So an explicit message is issued by the master device. And I don't know if we've actually talked about this yet. We have master devices and slave devices. That is a bit of an old wording system at this point. I forget what the new words are for master slave. So let me see if I can quick look that up. Master slave. So we now have things like active and standby, writer, reader, parent, child, leader, follow, master and slave. This is all coming from a news article. Those weren't the terms that I was looking for. I saw different terms at some point, but anyway, the master device is the one that's controlling it. Teacher, student, you want to go with that one? That's what we are, right? So the teacher is the one that's sending out the questions and answers and expecting responses from the students. Hint, hint, wink, wink. I ask questions, right? They have, traditionally, there's two explicit messages. There is a get and a set. So the get is me saying, hey, give me this information, whether it's a temperature sensor or a button press or whatever the case is. Or a set is me saying, turn this output on, type of thing. All right. Now, we only have, I think it's 8 bits traditionally of information we can send at a time. All right. That's not a lot of information, but that's okay. There is a way to fragment that if you need to send more, say 16 or 32. But anyway, where was I going with this? Oh, no matter what, if I'm sending a message to you, an explicit message, the slave devices, I'm just going to keep using that terminology because that's what I'm used to, it is expecting a response from you. So the master is saying, hey, get this information. It's expecting you to send something. If I say set, it's expecting you to say done it type of thing. All right. Now, if I do send that fragmented message, so I've sent you 32 bits over a bunch of packets because I'm linking them 8 bits at a time. You would think it'd be 4, but it's more because of the whole fragmentation process. You have to actually respond to every 8 bits, basically saying got it, and before I would send the next ones, I'd have to get your message saying I got it back, type of thing. So kind of annoying in that aspect of things. But anyway, so that's explicit messages. You might also have I/O messages, and these are messages that are transferred predefined I/O data between a Devicenet master and a Devicenet slave. And as I said, those are predefined. And then back to that peer message things. Peer messages are device to device, not a master to slave. All right, you're peers, right? You don't have someone that's higher up on the scale. And because of that, there is the standard never sets a predefined way for them to talk. So if you're doing Alan Bradley to Alan Bradley, they're doing peer messages, you're probably fine. If you're doing Alan Bradley to some other device manufacturer who's using Devicenet, you might not be able to do a peer message with them because my message type and your message type might not be the same. For example, I'm trying to send you a temperature reading, and I send it to you, and you get this information. You're like, I got the value 64. What the hell does that mean? Is that in Fahrenheit or Celsius? Is that 16 bits of information, or is there another packet coming with 32 bits? Is that scaled or unscaled? So because there's no predefined structure here, it's very hard to set up this communication, which is why it's overall kind of impossible to do. So that's why the explicit messages are really the way to go. It just allows you to have everything standardized. So as said, no well-defined rule for data exchange. Now I added this, oh, no, go back. There we go. I added this flavors part down here at the bottom, all right, which is weird to me, but this is how the website, how it called it, flavors. It's like, you know what, I'm just gonna stick with it. And we have polled and cyclic, and cyclic is spelled wrong. I have an extra E on there, so sorry about that. But anyway, oh, there's one more, change of state. But anyway, polled messages. This is a request/reply. So this is sent by the scanner at the rate of its choosing. So that master device is saying, hey, give me this information. And it's going, okay, here you go back. You know, polled. So I'm sending out a request, I'm getting a response. Cyclic is a scheduled messaging type. So this is me saying, every second, send me your temperature value, type of thing. So the slave devices will periodically issue messages to the master at some scheduled rate. And then we also have a change of state option. And this is when like you get a button press, that e-stop that gets pressed. And we've set it up you saying, that e-stop gets pressed, notify me right away because the building's on fire, you know? So whenever that I/O device, that slave device would say, this e-stop's been pressed, it's going, hey, PLC, e-stop type of thing going on, all right? So whenever that specific event that's been pre-programmed happens, that's when a change of state will happen. Now, on top of that, you will also have, for a change of state option, you will have a heartbeat. And what do I mean by a heartbeat? If someone checks your heartbeat, what do they normally? Okay, well, yeah, okay, you have your pulse. If you're laying there on the ground unconscious, someone checks your heartbeat. Why are they doing that? To make sure you're still alive. All right. Same exact rules go on here in the world of digital communication with heartbeats. A heartbeat is just me saying, hey, PLC, yep, I'm still here. All right. Because if all you're looking for is that e-stop to get pressed, well, I'm hoping at my industrial factory that e-stop never gets pressed. Right? That's my goal, is that e-stop, no one has any need to press it. So that heartbeat is that device saying, yep, no, haven't been pressed yet, type of thing. And it just happens periodically, so that way the system knows hasn't lost connection to that device, because, well, if that e-stop button doesn't work, well, someone's going to lose an arm. Because they're going to hit that e-stop, expect the machine to stop eating their hand, and it's not going to, and they're just going to keep getting pulled into whatever crusher, pulverizer, whatever device it is. And, well, now they're just lost their arm type of game. So, yeah. So that would be your different types of flavors of message, as this website called it. I'd call it like communication systems or something like that, but they call it flavors. Now here we have a somewhat standard topology, all right? I mean, I'd even take this to say, I mean, this includes like every type of topology that there is for a Devicenet one. So up at the very top, and you can see we got this nice thick line up here. That would be what is called our trunk line. So that is the main run from end to end. All right. And so where, this would be like at the beginning of your conveyor belt. This would be at the end of your conveyor belt. And in each of those, we need a terminating resistor. Now, do you remember why we need a terminating resistor? Correct. All right. So without a resistor at the end, the signal is going to hit the end of the wire, and some of it's going to get reflected back, which will wreak havoc with things. By putting a terminating resistor on the end, it makes it appear to the signal like that wire is infinitely long, and that resistor is going to just kind of dissipate that signal into heat, so it's not going to get reflected back. So that terminating resistor is very important in the long run. Now, to me, it's a little weird that you only have terminating resistors on the trunk line. If you've noticed that, there's on all of those drop lines. So the drop line are all of these other little itty-bitty wires. There's no terminating resistors there. So I don't know if the devices at the end are good enough or what, but that's what's going on there. So we have different types of drop lines. So you can see you just have single device on it. You've got, truthfully, this type and this type are the same thing in the long run, right? It's just, this one we have like a main drop line that has nodes coming off of it. This one, the drop line splits the 3 different devices. Now over here, I'd say we actually do have something a little different because you can see the drop line goes into each node. All right. However, you can still unplug any of these nodes at a time without destroying the network. Because even though this looks to me like the wire is going into that node, right? And then you think if I unplug that, it's going to unplug the network. Well, really, it's just you have, whatever your connector is. We're going to call it this big like square here, right, with 4 pins on it. Well, you really have the wires all connected here and on the back, so they're actually kind of just like going straight through that connector. So even though that connector does plug right into the node, it's not like you have one wire coming into the node and the second wire coming out of the node. No, it's still that same wire. It just continues right through the node. So in the long run, all these drop lines are actually the same. It's just how they look, basically. That terminating resistor at the end. Devicenet specifies that to be 120 ohm at a 1.4 watt. All right. That's not a huge resistor, but it's a pretty good size. Like you guys might be used to, like your traditional little wire round resistors, which look kind of something like a bean. Like that, and you've got 4 stripes on them. I feel like most of the time those are like quarter watt or less. So 1.4 watt, that's a pretty big resistor in the long run. Just again, it's kind of something to be aware of in the long run. These drop lines, they can be up to 20 feet in length. Up to 20 feet for those drop lines. All right. Yeah. You cannot exceed your max drop line budget. Now, I'm not 100% sure because I don't remember if 20 feet is your max drop line budget or if there's a different drop line budget. It does say this is speed dependent. So depending on which speed you are, your drop line budget will vary. So something to be aware of. So you can't have just infinite number of drop lines. You can't have your trunk line with 20 feet for every device. I don't know why you want to do that anyway, but you can't do it. So you do have to get your trunk line somewhat close to all these devices so you don't have super long drop lines. So just something to be aware of. Now for your cables. So we have thick, thin, and flat. All right. And you will see that depending on the cable type, if you look at our charts over here on the right, we have thick at the very top. And notice that we have 125 K-band, kilobaud, and that's 500 meters. For thin, that's only 100 meters. And for flat, that's 420. Yeah, that to me is just weird, but that's okay. So that does affect things. Oh, here we have our cumulative drops too. So Here's our drop line budget right there. Notice that the max drop length for each one is all 20 foot. That is consistent. But depending on whether you're thick, thin, or flat wire for your drop lines, I guess, the cumulative drop length is going to be changing slightly. So something to be aware of in the long run. So the thick or flat cable is used for long distance and is strong and more resilient than the thin cable. And if we just look at the max distances for the trunk, you can tell that thicker, flat, that's going to be the way to go. Thin cable is mainly used as the local drop line connecting nodes to the main trunk. So you're going to have like one big ballsy connection running from end to end, then you can run the thinner cable off of that. So thick cable is used when the trunk line length is important. Overall diameter of that is going to be roughly 1/2 inch. And we're going to have our signal wires are going to be 18 gauge twisted pair. And you don't see that very well in that picture. I thought you did. And our power wires are going to be 15 gauge. Now, quick question. Which one's bigger, 15 or 18? Which has a larger diameter for wire? What? Yep, the 15 is larger. All right, we're talking AWG, American Wire Gauge. Anytime you hear the word gauge, smaller is bigger. The lower the number, the bigger it is. All right, and this goes for anything with the word gauge. Needles. If you're getting an injection, you hear, oh, it's a certain gauge needle that they're going to have to use. That tells you, yeah. I need a double lot needle, to inject something. Yeah, monsters needle. If you have anybody that does the earrings where had the hole freaking through their ear, that is gauge as well. All right, so it's inversely, which to me is weird, but I hate it. I'm like, why do we have to do this? And I'm sure there's some reason why, how they calculated it and took the square root of the block. I don't know, but I hate that it's backwards. It's one of those lovely games when you guys are like trying to remember, wire gauge is inverse. And you're like, oh, it's just backwards. Just remember it's backwards. And you're trying to remember all these things, and this one's backwards, and that one's not backwards. It's like, one's which again? It sucks. But anyway, thick cable has a max, that 15 gauge. We're only allowed to do 8 amps of capacity of power on that. So that's a good bit. You're not like you're going to be powering your contactors or things most likely off this, but it's enough to keep the I/O devices running. So it is something that you do need to be aware of, though. We're going to have some polypropylene fillers in here to help with strength of the wire, basically, if I had to guess. And then we also have a copper shield on the outside. So there's a lot going on in there. And if we actually do look at this real closely, this even tells us that the red and black wires are our power, and blue and white are our data pair. So it even tells you colors of what should be in there. Now, could you grab any random 4 wires off the shelf and make one of these? Yes. All right, there is no reason you had to absolutely use these wires other than probably that the standard says you will use these 3 options, but you could make your own. All right, thin cables that we're using for drop lines or short trunks, roughly 1/4 inch in diameter. Signal pair wires, they're only 24 gauge. Power lines are only 22 gauge. And that's only 3 amps. So we've halved our capacity there. Flat cable, this is not twisted. That's just kind of a big deal. Twisting helps reduce interference. So that's how we like twisting things nowadays. Now, I will say, also for these, not only is it twisted for the thick and the thin, but you also have shielding on the outside, at least of the thick. That will also help reduce interference if you ground it correctly. So a little bit of give and take going on there. Flat cable, which is, do I have a picture on the next page? No, I don't. It's, if you would look at it at the end, is basically just wire with a little bit of, plastic going between them. That's all it is. It's 8 amp rated, no twisting, no shielding. However, it's highly flexible because of that. So back to the whole world of give and take going on. You want shielding or do you want flexibility? Don't you just love the industrial world? You're going to go with option A, B, C, or D. You're like, well, which one's the best? Well, A is the best in this situation, B is the best in this, C is in this, and D is in this. Well, I don't really follow any of those specific categories. Well, pick one. All right, so that is that. Now, here I have a whole bunch of different taps showing for you guys. So, if you were doing a round trunk line, you may be using this type of connector up at the top here. All right, so that's a round connector. You've got a little knurled connection that actually screws on to the other part. So that is, to me, a big benefit. It's actual stress retention, release, whatever. You're not relying on the wires to hold the wire in place. You're relying on a connector that's connected to the sheeting. So that is much better. But anyway, we've got, this would be a multi-port tap. And this, as it says right there, is sealed. All right. So all those probably have little gaskets on them or O-rings or something. So that could be in a harsh environment. So that way you're not going to have crap getting into it. So that's a big win. You have a T-tap, which is what we have over here on the right. Or down here, I think this was also, I would call that a T in the long run, but maybe other people wouldn't. That would just be a drop line, I guess they're calling it. But anyway, notice you're probably are going to have one screw-on connection, and then probably other ones that have, this would be the call that the male, and this would be the female side. All right, so you're only going to have one of the one and multiples of the other. So that way you can have just extension cables that have, male on one and female on the other, and you can connect all these things together. So it makes your life kind of easy in that aspect of things. So that was a multi-port. Yeah. So here you have, this is really weird. This really confuses me. But anyway, here you have, this is the connector that would get plugged right into our PLC. If I had those PLCs down here, I'd show you them right now. But literally, that connector plugs right into the PLC. And then there are little slots for you to screw the wires to on the top. And there you can see the screws for it to tighten those, those connections down. And on the bottom, there's more screws. So you can actually tighten two wires to this without having to twist them together and shove them in the same slot, which is really nice because you don't have to do that. It's just weird to me because you don't see that type of connection very often. But because of how this is designed, they're expecting you to go device to device to device. They said, we need to be able to put two wires into this connector, and they didn't want to make you twist them together. So this is the system they came up with, which to me is actually kind of nice. So that was going on there. As I said, these top ones, these are sealed. These bottom ones, they're all open. So the wire's just kind of hanging out there. In a junction box or something, having open wire is not the end of the world. But if it's going to be outside of a junction box or a control cabinet, the sealed ones would probably be your better option. Having said that, this top one, I would say these are all going to be the round type. This is going to be a round cable, as you can kind of see in the picture, where the open ones could be round or flat cable. So again, a little bit of give and take going on there. All right, some power requirements here. You want a dedicated power supply just for your device net. All right. We talked about how 8 amps is the max current that you're probably going to be feeding on the network. All right, because that was the max that the cable, either the thick round or the flat line would accept, basically due to lengths and things like that. So you want your own dedicated power supply. You don't want the one that's running your PLC to also be running your device network and all those other wonderful things. You are allowed to change cable types as you go through your network. So you could have a thick connection as your trunk and a thin for all your drops or whatever the case is. That is perfectly fine. Yeah. Anyway, all right, so here we have a little example here. I have to remember how this works. As we get longer in length, notice that our max current that we can pull off this drops. All right. So, if we look at this, having these first two rows, they're both saying the same thing. One's just in meters, one's in feet. So you can just basically ignore it, and I'm just going to put a line through this, because we all like feet, right? We're in America. Feet are what we use. We should go to metric, but we're in America, so I'll stick with feet. But anyway, as you can see, that if you have a super long wire that is the 1600 feet, you can't be pulling 8 amps off at the far end of it. All right, you only can pull 0.63 amps, and you can see that it drops pretty freaking quickly. Like by the time you're up to our half length, you've lost almost 1/8 of your total power. So really, you want to keep your home runs as short as possible. So it is something that you want to think about. Yeah, it's basically the same. Thin, thick cable, thin. I don't know why this one goes up to 8 when the thin cable can only handle 3. So that's kind of weird. But anyway, so we have a total network length of 200 meters, and the sum of our nodes has to be less than 0.65 amps. So if you had 5 nodes and each one pulled 0.2 amps, and your network was 200 meters or 166 feet or 666 feet, 2 amps 5, 1 amp total, you'd be okay. But if you had a 500 meter or 1600 foot, you would only be able to pull 0.63 amps, so you'd be over budget now. So you do need to really keep that in the back of your mind. Now, you can have a center connected with a single power supply. All right. So this is assuming that you have, let me draw. Then there we go. This is assuming that you've got your power supply here and your cable goes this way and ends all the way out there. If you were to put your power supply in the middle, now you have your network length can be kind of different, because now you might still have that same 1600 feet, but if this one's we'll say 1200 of it and this one's 400 of it, well, 400 allows us to have 0.78 over here and 0.63 over there. No, 1200. Yeah, like 0.8. Anyway, 400's all the way. I was looking at meters. I gotta look at feet. Darn it. Let's redo this. 500, so that'd be 2.01, and 500 feet and 1200 feet short. That's a little over. So we'll go 11. That gets us to 16. So you'd have 11, so 0.89. There we go, over there. All right. So you could have now put more power. You get almost that full 3 amps back. So where your power supply goes is very important in the long run. All right. So here we have a single-ended power supply connected. We have a 200 meter, 656 foot length. Our total current sum is 0.65 amps. So the only thing we have to question here is what type of wire are we using? All right. So if we look at these tables, which is the one we just did, we're doing 0.65 amps at 200 meters, 500 feet. So that would be here. Or our meters here is a lot less. 200 meters, 605 feet. All right. Notice we don't have 200 meters as an option. All right. So assuming we use thick cable, we would be fine. We would fall within the regulations. If we use thin, it wouldn't qualify because we don't have enough cable length to be able to do that. We can't even go past 100 meters with the thin stuff. So a little bit of give and take going on there. So down here, we've got our little example. So node 1 is 100 milliamps, 2 is 150, 3 is 50, 4 is 260, 5 is 100. So 1, 250, 300, 4, 5, 550, 650. So that's exactly what we've got going on here. So notice it says thick cable, meet the requirements. However, if we come to this one, we've got our power tap in the middle. Tell me, you can ignore all of this. Use just based on this picture over here. Do we meet the requirements based on those tables? Do we have too much power? My question is, do we have too much power flowing over that 90 meters or over that 120 meters, according to the tables above? All right, so looking at this, we've got a length of 90 meters. So let's assume we're going to be doing this on the main one. Doesn't tell us thick or thin, but I would assume thick at this point. 90 meters, we're going to ground it up to 100 just to make our life easy. So we're allowed 2.93 amps on that section. We have 1.05. That one, 2.93 is greater, right? We're in the clear. All right. We look at the other one. We got 120 meters. We'll round that up to 150 to make our life easy. We're allowed 2.01. We have 1.88. Are we in the clear? Yep, we're in the clear. They're both less, so they both meet the requirements. Again, if we would assume that we are using thin wire, not thick, for this left section, 90 meters right there, we're only allowed 0.78. 1.05 is greater than that 0.78, so that one would not qualify if we were using the thin. But we're not, we're using the thick. So, yeah, if we're using thin, we'd be screwed. But if we're using the thick, we're fine. All right, so again, little bit of give and take going on here is really what it comes down to. All right. So here we've got some sister power limits. So max voltage drop on both the minus VE and the positive. So on the voltage lines, we can have up to a 5 volt on each line. All right, so that is something to think about. That comes down to your resistivity, right? So if you're using random scraps of wire and you're like, okay, what's my voltage drop over this? So I'm going to put 25 volts in at whatever amperage, you can calculate your voltage drop because you know the resistivity of the wire and you can calculate how much amperage you're going to be losing or how much voltage you're going to lose based on the amperage. So that is where that 5 volts comes from. All right. Thick cable, we already said 8, thin is 3. We've already talked about that. Max current for the drop line is around to be 0.75 to 3 amps. That's a pretty big range. Voltage range at each node. So each node has to see a minimum of 11 volts, but we're allowed to go up to 25. Most likely you're going to be feeding a 24 volt power supply into this. So unless you like tweak the little adjuster value up a little bit, you're going to be 24 volts is what we're going to be using. And then each product is going to have its own specific manufacturer stuff. So we talk, yes. So when you're figuring all this out, what wire are you using? Are you going to meet the code? Yada yada yada. To help keep you from having errors, for configuring of your power in your network, you want to do a few things. One, ensure your calculations made for current and distances are correct. Be conservative. All right, remember on the last slide I was like, yeah, 140 meters. Let's use 150 meter one. Like, just add a little extra length because line of sight. This is the other thing. If I go straight from me to you guys, it might be what, 15 feet thereabouts. But if I have to go up, over, and down, especially in this lab, I've literally just doubled my length of wire, if not tripled it, because of how high the ceiling is. Like having to go up and over things because you're like, oh, we have these nice wire tracks over all the equipment that we can run things down, which is great. But you're adding length, so you have to go up to get to that. So your main trunk line is going to go from you up across the top and then back down. So even though you're like line of sight is this, it's a lot farther when you have to go up and go around things. My favorite example of that is on Google Maps. You're like, oh, how far is this from me? It's like, oh, it's 14 miles from home. And you're like, okay, navigate me there. It's like 20 miles. You're like, you just told me it was 14 miles to that, but it's 20 miles for me to drive there? Well, it's because I gave you a distance that was as the bird flies, or as the crow flies, right? It's just a straight line straight from me to you. But driving, very rarely do we have that beautiful straight line. Normally you've got to go a little east to then come back a little west or north or south or whatever to go from point A to point B. So anytime you have to add that distance in it adds up a lot. It's one of those things that I've noticed over my years. So be conservative with your distances. Make sure you're taking your vertical heights into account there. Conduct a network survey to verify correct voltages. Remembering 11 is the minimum at each node. And a max voltage drop of 10 volts across each node is allowed. Allow for a good margin of reserve power. So if you're going to buy a power supply, and that last example said you needed 2.8 amps, don't buy a 2.8 amp power supply. Add an extra, 10% to that. buy a 3 amp power supply, a 5 amp. All right. Just a reminder, anytime you're buying a power supply, it's always going to have two things. It's going to have your voltage and it's going to have your current. Voltage and current. Whatever the voltage is supplied. No, is given. All right. So if whatever device you hook up to that, it is getting that voltage. So if you have a 40 amp or 40 volt power supply, if I plug my phone into it, it's getting the full 40 volts. My phone's not like, yo, bro, I only need 5 volts. It's like, I don't care, here's 40. All right. However, on the current side of things, you could have a freaking 100 amp power supply. And my phone's like, I only want 1. And it's like, all right, here's 1 amp. All right. So voltage is supplied. No, it's given. It always flipped. It's given. I am giving this voltage to you. Whether you like it or not, you're getting that voltage. Current is supplied. It's like, you want some amperage? I got some. You can have it. You don't have to have it all. You can just take a sip. All right. So it's better to overbuild a power supply. Now, the only downside to overbuilding a power supply, literally the only downside, is probably the cost and efficiency. If you have a power supply that's meant for 100 amps and you're pulling 2 off of it, it might only be doing that at like 60% efficiency. If you're pulling 80 amps off of it, it may be doing that at like 97% efficiency. So a little bit of give and take going on here. A great example of this is computer power supplies. If you guys aren't building computers, you don't know a lot about them, they have standards. There's 80 plus gold and silver and titanium and I think platinum as well. And like gold, I think is like 80% or higher. Titanium's like 95 or something. I don't remember where the percentages are. But it's assuming so much of a load on that power supply. So it's like, yeah, you bought a 1,000-watt power supply. You can run basically anything on that computer. But you're only pulling 200 watts off it. You're not getting the full efficiency out at that point. The efficiency is at like 80% load or something like that. Otherwise, the graph does something like this. And at 100%, it's not 100%. It's not as efficient as it gets either. So it's like the sweet spot is like 80 or something like that. I don't know magic numbers. But yeah, so cost of the power supply and efficiency. Those are the only two things that you're losing by buying too large of a power supply. But in the long run, buying a bigger one, it'll probably have a better lifespan because you are not beating it up as much. You're not heating those MOSFETs up and requiring the fan to spin. So you're not putting as much heat into it, so the components will last longer. So you might pay extra up front, but you're not gonna have to replace it as quickly. It's a lovely game, isn't it? If you're using multiple power supplies, so like different ends of the network, so you just don't have the power cables, the 24-volt line connected. Again, ground has to be connected, but not the 24-volt. It's essential they must all be turned on simultaneously to prevent from overloading. If you do have multiple connected, you're not supposed to be, but be way aware of. Yeah, you gotta have them isolated from the AC supply and the chassis. Just kind of a warning. All right, and the last thing that I've got for today, we'll have more next class, is fragmentation. So this comes back to the you're only allowed to send 8 bytes of information. This is bytes, not bits. All right, I said bits earlier. It's bytes. All right, so that's actually 64 bits. But if you need to send more than that, because you're like, hey, I need all of these I/O, it's 80 of them or whatever. You need multiple bytes, which is fine. They came up with a system for this. So these first numbers here, these are telling you the order of the packets. So the first fragment number is always going to be 0, 0. The last fragment number is always going to be in the 80 to the FF range. All right. And the intermediate fragments are always going to be from 41 to 7F. That's just the way the game works. That's the system they came up with. So you only can send 8 bytes. And somewhere I had that you're only getting 6 bytes of data then being sent, because I think it's fragmentation information, then device ID, and then it's 6 bytes of data. All right. So you're only getting 6 bytes per message now instead of 7 or 8 or whatever the magical number is. So probably 7. So just something to be aware of. That is probably why we're missing this gap here. Because that gap would be if you're not fragmentating and you're just sending a device ID. You're like, hey, device number 1, I need to talk to you. All right, that would fit this gap. So that would get you 7 bytes of data for a normal packet. And then when you're like, oh, I'm fragmenting now it's fragmentation information, fragmentation, then ID, and then 6 bytes of data. And then you'd send a response, got that, and then I'd send the next one. So 41 ID data. And the next one, 42, 43. And then when I get to the end, I go, like, okay, 83, this is the last one. We're good to go. Whew. All right, that's it for this one.